All right, let's take a look at this a little bit. We're going to talk about some kind of special ideals. A prime ideal is a proper ideal such that if you have any two ring elements, if you multiply them together and you're in the ring, then one of them had to be in the ring to begin with. So let me just say briefly what we're talking about. So if you take a standard examples like pz, so for instance, let's look at 5z, which is set of all 5 times n such that n belongs to integers. Well, if I have a times b belongs to 5z, that means that a times b equals 5n for some n. Well, how can you get a 5, right? So 5 divides this side, so 5 divides a and b. Well, you can't have a little bit of 5 in a and a little bit of 5 in b. You either have to have 5 divides a or 5 divides b, in which case a is equal to 5m or b is equal to 5l, and either a was in I or b was in I to begin with, but not both. And notice that that's called a prime ideal because this isn't necessarily true with other ideals. So this is an ideal of z that corresponds to a prime number. If you look at 6z, it doesn't work out. For instance, 2 times 3 is in 6z, but 2 is not in 6z because it's not a multiple of 6, and 3 is not because it's not in a multiple of 6. But when you combine them, you can get a composite number. But that's not true with primes, so that's why we're calling them prime ideals. Yeah, I'm just going to give you the same example here. This has just been done more like so. Prime divides the right side, so prime divides AB. Prime numbers, though, one of those has to be prime divisible by a p already. So we already have one of those. All right, moving on. Here's the same non-example. All right, so here's another interesting example. Let's look at the polynomials with integer coefficients. And I'm going to let the ideal be, it has to have not a 0 for a constant term. There can't be a constant term. So x squared minus x is in I, but if I added 7 to it, then it's not an I. So f and g are like this. Are there elements such that you multiply together to give them that? Then you have to have, because the only way, this is just talking about the constant term, when I multiply together these two, the constant term is going to be these two multiplied together. But the only way, z doesn't have any zero divisors, and this is an element of z. So if I have something in z, an integer times another integer equaling 0, one of them had to be 0 already. Which means that if a is 0, that means that f was already an I. If b is 0, then g was already an I. So what does this mean? This means that this ideal here is what we call a prime ideal. It's another example of a prime ideal. So let's suppose we have a ring with unity and I is an ideal. R mod I is an integral domain if and only if I is a prime ideal. So we're looking at quotient rings again. And we can see that we only get a quotient that's an integral domain, that is no zero divisors, if and only if I is a prime ideal. Here's a proof. Suppose we have an integral. And let's see. If we have a and b multiplying together to give me I, then if I multiply them together, I get I plus ab plus 0. Remember, I is the identity. But Ri has no zero divisors. So if I have two things together, they multiply together to give me 0, because this is really the 0 element of the quotient ring, that means that one of them had to be 0 already. Either a plus I equals, in which case a is an I, or the other way, or b is an I. So that's exactly what it means to be a prime ideal. So I is a prime ideal. If you have the quotient as an integral domain, then I is a prime ideal. Let's go the other way. You have a prime ideal, a and b. Let's see if we can have a zero divisor in the quotient. So if you multiply them together and you get that, well, this product is defined to be this. And if this is equal to that, that means that ab is an I. But I is prime. So that means that either a was an I or b is an I. That's what it means to be a prime ideal. So what does that mean? that means no zero. Because either a, if a is an I, that means a plus I is equal to a plus 0. And if b is an I, then we get that. And one of these was 0 to begin with. So we get an integral domain. So a maximal ideal of we'll look at a commutative ring, is a proper ideal. So it can't be all of R. Right, because R is kind of a stupid ideal. So we have I is not equal to R. That's what proper means. Such that if you have a bigger ideal, then either A is equal to the ideal or R. So R is up there. Your ideal is proper down there. If A is somewhere in between, that means either you have to be the whole thing, A is equal to R, or A is equal to I. There's no bigger ideal than I except for the entire ring. That's what maximal ideal means. Bigger in the sense of containment, maybe I should say. So example, let PZ is a maximal ideal. So, 101Z is a maximal ideal. So is 2Z. But there are more elements in some sense in 2Z than there are 101Z. They're both infinite, but in some sense you can see there are more elements because there are like 50 elements in 2Z that are less than 100, and there are 0 elements, or there's 1 element of 2Z of 101Z that's less than 100. So in some sense there's more. But we're talking about containment. So watch this. If A is an ideal that properly contains PZ, in other words, if we have PZ and we have Z, right? These are not the same. Let's suppose that A is strictly bigger. I'm going to show that everything is in. I'm going to show that these two have to be equal. So pick an element that's in A but not in I. P can't divide A, because otherwise A would be in PZ, and we just picked A to not be in PZ. That's PZ. So the GCD of A and P is, we can use the Euclidean algorithm to get a sum of these that equal 1. And now we have A and P are in an ideal. Why is P in A? Well, because A contains PZ and P is in there. So A is an ideal, so whenever I multiply anything that's an A, like A by anything else, you stay in A. Similarly, P is in A, so by the absorption property, PM is an A. That means that 1 is an A. But what does that mean? I can use the absorption property to show that A is equal to the integers now. Right? Because if 1 is in here, that I'll let Z belong to Z. Then Z equals 1 times Z belongs to A by the absorption property. So that means that the rings that we get containment, and so Z equals A. A non-example, let's look at 6Z. 6Z is an ideal, but it's contained in the evens. And the evens isn't all of it. So 6Z, there's a bigger one that contains it. Whereas PZ, for instance 2Z, there's nothing bigger. So that's going to be maximal. This is not maximal. 6Z is not maximal because I can find a bigger one that contains it. All right, another example. Polynomials, where the constant term is even. Suppose you have a bigger ideal. But then there would be a polynomial that's in this bigger ideal that is not, that doesn't have even constant term. So it doesn't have even constant term, so the constant term is odd. So take any polynomial now. When I multiply it by G, I'm going to be in the ideal A. Either H not as even, or if H of 0 is even, then H of 0 is an I, but I is contained in A. So H of X is going to be an A. Or if it's odd, then H minus G is going to be an I. Because if you subtract them, you get H is going to be like HN, XN, plus da-da-da, plus H naught, which we know is odd. If I subtract that, if I get GM, XM, plus da-da-da, plus G naught, and that's odd. When I subtract them, here I get a whole bunch of X stuff, who cares? I'm going to get h naught minus g naught, and odd minus an odd gives me an even. And if the constant term is even, we're in I. So h of x, which equals the sum of these two, is an A. Why is that? Well, g of x is an A, because I picked it to be an A. And the subtraction is going to be even, which is an I, which is contained in. So h of x is an A for all A, so we get equality here. So therefore, this is a maximal ideal. There's no ideal that's bigger. If we had one that's bigger, it's going to be non-proper. Therefore, I is maximal. Note that if you require not that the constant term be even, but it be 0, that's contained in even, because 0 is an even number. So this is not a maximal ideal. K is not maximal, but I is. We already saw that K is prime, though. So K is prime, but not maximal. All right, let's take a look. We have a commutative ring with unity, and I is an ideal. We get a field. The quotient is a field if and only if I is a maximal. Let's prove this. Suppose we have a field, and suppose A is an ideal that properly contains I. So I'm going to assume that I is a field, and I'm going to prove that I is maximal. So if A is an ideal that properly contains I, I'm going to show that A is equal to R. If I can do that, then I'm done. I will have shown that I is maximal, if that's the case. So I'm going to let it properly contains it, so there's some element in A that's not an I. This is a non-zero element of R mod I. Why is it non-zero? Because A is not in I. So it has to have an inverse, a multiplicative inverse. So B is equal to A inverse here. So this is what I get. And so subtracting both sides, I get that this AB minus 1 is an element of I. And because it's an I, it's got to be an A, because A properly contains I. What happens next? A is an A. By the absorption property, AB is an A. So since I have this as an A and that's an A, 1, which equals this element of A minus the other element of A, has to be an A. Therefore, all of R is an A. Since R, for all R is equal to R times 1, and since 1 is an A, I can use the absorption property to get R as an A. So I get that A is equal to R. And what is it? A is an ideal that properly contains I. It's guaranteed to be the whole ring. That's exactly what it means to be a maximal ideal. So I is maximal. So I prove this direction. If you have a field, then you get a maximal ideal. Then I must have been maximal. Next, we'll prove the other direction. So I'm going to prove that R mod I is a field. That's what I need to prove. So let B be outside of I. I'm going to show that this has an inverse. Okay, sorry, I'm going to show that this has an inverse, actually. Multiplicative inverse. So let's see. I'm going to pick an A that is defined to be this. And this is an ideal. How can you verify it? Well, if you subtract two elements, A plus BR minus A prime plus, A prime BR prime, you're going to get, if you do a little rearrangement, A minus A prime plus B, sorry, I did this wrong, R minus R prime times B. Well, what do I know? I is an ideal, so if I start off with two elements in an ideal and I subtract them, I'm going to stay in I. So I still get an element of I right there. And what happens to B? I still get an element of B. Maybe I'll move it over there because it's a commutative ring. And R minus R prime is still an element of R. So when I subtract two things, I stay inside of A. So A is a subrung. And now what happens if I multiply any element of this by an element T? Well, I'm going to get AT plus BRT. That's almost my name. AT is an A by the absorption property of A. So therefore, I still get an element in A there. And then I still get B times some element of the ring, because this is going to be some element of the ring. So I get the absorption property. So we're happy. A isn't ideal. Since I is maximal, and A is going to contain I. Why does A contain I? Well, because A plus B times 0 is an A for all A belong to I. So that means that I is contained in A. And since I is maximal, A has to equal R, because I'm assuming that I is the maximal ideal. So every element of R can be written like this, and 1 is in R, so 1 is in A, the unity. So 1 is equal to like this. Then the unity of the quotient is equal to this, and the A gets sucked in by the coset properties. I get that A is equal to 1 plus BR, which equals I plus B, I plus R. But that means that I plus B has a multiplicative inverse. So I plus B inverse is going to equal 1 plus R, because when I multiply them together, I get the unity. And we're done. Wasn't that cool? Thanks.